Okay, so now I'm going to go over question 25, and the first important concept in question 25 is angular momentum. Okay, so basically angular momentum, there's two types. There's L, which is the variable we use for angular momentum, equals I, moment of inertia, times angular velocity, and L equals mass times velocity times the radius. And this is the latter one that I just explained is the one we're going to be using in this problem. So I'll just write that. And basically this is when an object is circling around something else. So not the object itself is rotating around its axis, but it's rotating around another object. So that's what we're going to use here. And then the second concept I'm going to go over is positive and negative angular momentum. So if an object is going counterclockwise, it will have, or rotating counterclockwise, it will have positive angular momentum. And if it rotates clockwise in the clockwise direction, then it will have negative angular momentum. So I'm just going to write that here. Clockwise equals negative that. Counter, I'll just write counter equals positive. Okay, so those two concepts are going to be important when solving question 25. Okay, so now I'm going to read question 25. Two satellites of masses m1 and m2 orbit a planet of mass m in circular orbits. The satellites travel in opposite directions with speeds v1 and v2, as shown in the figure above. Their orbital radii are r1 and r2, respectively. Assume that m is greater than m2, which is greater than m1. Okay, question 25 specifically. The magnitude of the angular momentum of the two satellite system is best represented by. Okay, so first I'm going to draw the picture in order to explain it. So I'm going to draw it right here. So there is a two orbital system. This is the outside orbit, this is the inside orbit. And mass 2 is rotating this way with velocity 2, and mass 1 going at 1, and this is the planet, mass m, this is r1, radius 1, and r2. Okay, so in this problem it is asking for the angular momentum of the two satellite systems. So we're going to use MVR because it's rotating around something else. And first let's find the angular momentum of the inside. So here, so L is equal to m times v times r, and we're using mass 1 for the inside, velocity 1, and r1. And when we look here, it is rotating in the counterclockwise motion. And we can see that because the velocity is going this direction, which is counterclockwise. So this will be positive. So I'll just put here like positive. So we know that since it's going counterclockwise, it will have positive angular momentum. Okay, so for the second one, this orbit here, L equals m times v times r, and then we can do mass 2 times velocity 2 times radius 2. And when I look here, I see that here it's going clockwise because velocity 2 is going like this, which is the clockwise motion. So that means this will be negative. So I'm going to put a negative sign here. So if we're trying to find the magnitude of the angular momentum, the total magnitude for the whole thing will be m1 v1 r1, and then plus negative, it's going clockwise, m2 v2 r2. And with this can also be expressed as m1 v1 r1 minus m2 v2 r2. And so that means the correct answer to this question is D. Because that's the answer. So in conclusion, this problem shows important concepts of angular momentum, and specifically when an object is going counterclockwise, it will have positive angular momentum, and when it's going clockwise, it will have negative angular momentum.